Thank you. Welcome back. Did you have a good lunch? Lunch was good. Yeah. Anyone hungry still? All right. So we were looking at this morning. I stated a theorem. Maybe we should look a little at the proof at some point today. So there are two types of representations which emerged from the theorem that we wrote. And type 1, so to speak, which is mostly about what this lecture is about, are the representations as the C-star algebra people would say, that are weakly contained. In one of these representations of G as translation operators, unitary translation operators, excuse me, on L2 G mod N. And at the moment, type 2 is all of the representations which are not in type 1. So by definition, a basic representation is all of the others. But we know something about these representations, because these representations, thanks to the main theorem, have something to do with compact operators. And so we know that they occur, as I explained at the very end, as sub-representations, two types of course, I'm talking about irreducible representations. And we're studying these so-called tempered representations. This is very important. They occur as sub-representations, as we discussed at the very end, of the standard regular representation on L2G. So we know right away, for example, it's not saying much, but we can say that the ones we're missing are not so many. There are countably many. But there could be 0 of them, so let's just say at most. Actually, yeah. If you think about it, for every compact group, every representation is basic. And if the compact group happened to be finite, then there would only be a finite number of basic representations. Apart from that case, all of the basic representations form a countable set. Oh, and just since I mentioned this earlier, I should mention it again. Technically speaking, the single element group is an example of an N. Technically speaking, G is a parabolic subgroup of itself. But we're in this theorem, we're not allowing this. It's not allowed. Even though it's a legitimate N of a legitimate parabolic subgroup, this theorem would not have any content if you allowed this. So we disallow this particular guy. Okay. And this afternoon, I want to say a bit more about both classes. Get to know these collections a little bit more so they can feel a little bit happy about them. All right, and we'll start with the basic representations. And we'll do that by just making another definition. Oh, we don't even need this. Do that later. Here's another definition which involves representations and compact Hilbert space operators and so on. I'll say that an irreducible tempered representation, tempered unitary representation, I'll say it's compact. You'll see why very soon. And here's what I should like to say. What I should like to say is that there's an ideal. An ideal in the reduced C-star algebra let's see. It complements the kernel of pi. So the C-star algebra of G is just a direct sum. It falls apart into two pieces that do not speak to each other. One is the kernel of pi, which is an ideal, and the other is this ideal that I'm talking about. And this other ideal should be mapped isomorphically to the compact operators, the C-star algebra of compact operators in the Hilbert space. So here's what happens. The C-star algebra, therefore, looks like a piece which is compact operators on H pi, and a piece which looks like the kernel of pi. And these two pieces, these two ideals, don't speak to each other in the sense that if you take any element in the first ideal and multiply it by any element in the second, you get 0. They're just completely disjoint. Okay. So one reason that you might call these representations compact is that the word compact appears right here. But a little more substantially, if G is compact, then every pi is compact in this sense. So these are the, I should like to say that these are the representations which behave as if the group were compact, even though the G itself might not be compact. G is one of our reductive groups, for example. It could be SL2R. Okay. In fact, we know that, according to the Peter-Weyl theorem, G breaks up as one of these C0 direct sums, as a bunch of copies of the compact operators. H pi is finite dimensional. Compact operator just means any operator on H pi, like that. So in a slightly different version, the C-star algebra version of the Peter-Weyl theorem says this. All right. Just by the by, this C-star algebra is mapped via pi onto the compact operators on H pi. There's also a map in the other direction which embeds this single summand back into here, and there's a well-known formula for this which was worked out back in the days of, I don't know, the theory of representation theory of finite groups worked out by Frobenius and Schur and so on. And it goes like this. So what you do is you take an operator T, which is an operator on this representation space. Let me just move this up so I can write this. And now I want to build an element of the C-star algebra. And so I'll show you what it is by describing it as a function, a continuous function on G. And I'll just send G to the, oops, now I need to leave a little bit of space. Leave a little space there. And what I'll do is build a function in this way. I'll take the trace of pi of G, happens to be the right thing to put an inverse there, and then T, like that, and we're almost done. There's a normalizing factor, which is kind of interesting, which is the dimension of pi over the volume of G. So when we build the C-star algebra, we have to choose a Haar measure, and maybe we chose it so that the volume was not 1, in which case this formula should be put in like that here. Okay. So this is a map which explicitly embeds a copy of the compact operators as an ideal, as it happens in the C-star algebra, and realizes this. Turns out that it's exactly complementary to the kernel of pi. This is what's proved in the theory of finite groups or compact groups. It's part of the theory worked out by Peter and Weil. And if you want to Google it, then you should look up Schur orthogonality. Which says that this funny map is actually an algebra homomorphism from this algebra of matrices here into this convolution algebra of functions. That was worked out by the great giants of history, Frobenius or Schur, or I don't know, someone like that. All right, now back to infinite dimensions. So if you have a compact representation, on this ideal, I'll always just write this ideal as k of h pi. The actual formula for the embedding, here it's just supposed to exist, that there should be this complemented ideal, blah, 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 blah. The actual formula can be a little bit interesting. Here it involves some numerical normalizing factor. But in any case, there is guaranteed to be an ideal in here which is complementary to the kernel. Okay. So we could take the regular representation and just restrict it to this ideal. And then it's a representation of this compact operator algebra as bounded operators on L2 of G. Okay. Now, if you have any representation of the compact operators, it's always a direct sum of irreducible representations. Now, it could be that this is not exactly a legitimate representation in our sense. Remember, that when we're talking about representations, we require, according to our definitions, this non-degeneracy condition. And that may fail if you just restrict a non-degenerate representation to a subalgebra. Maybe it will be degenerate. If it is degenerate, it just means that you can write the Hilbert space as this subspace direct sum some orthogonal complement on which AX is 0. So you may have to throw away some big 0 piece. But what's left is just a direct sum of irreducible representations. And so what you find is that H pi embeds as a subrepresentation of L2 of G. It's by this abstract C-star algebra stuff. And of course, Peter and Val knew this for compact groups. They described, as I mentioned before lunch, L2 of G explicitly in terms of its, so to speak, Fourier decomposition. And so these have some of the same flavor to them. All right. A lot is known about representations which embed as irreducible representations which embed as sub-representations of L2 of G. These are very familiar in representation theory. And don't need to know a great deal about them, but it's, let me just mention one thing, which is that they are square integrable. In fact, they are exactly the square integrable representations. And what that means is that for every vectors v and w in Hilbert space, pi, this function which sends g, the so-called matrix coefficient function, which does this, belongs to L2 of G. And there's a beautiful resonance with this nice fact that was worked out by the ancients. Associated to this representation, this is what, I'm not sure, essentially this is part of the theory worked out by von Neumann. I'm not sure Gautama, Harishchandra, or someone worked out these things as they apply here. Each representation has a formal degree, which is unique, so that what I'm going to do is I'm going to write down exactly this formula here, and the one problematic part of this formula, or the most problematic part, I'm going to replace by d pi. In the case where G is not compact, in the general case we're now discussing, the dimension of the representation is going to be infinite. On the other hand, the volume is also going to be infinite. And when you divide these two infinities, what you get is this renormalized dimension here. And then it's exactly the same thing. Oops, sorry, I'm writing down the wrong version of it. What I wanted to do is write down, as I said, exactly the same thing, and then I screwed it up. So here I want to take the trace of t times pi to the inverse. Well, for this formula to make sense, you need to be dealing with operators for which there is a trace here. So one could start off with the so-called algebra of trace class operators, the operators which have a sensible trace. Some of the diagonal elements. And where you end up, well, in general, where you end up, all you can say in general is, if we're talking about square integrable representations, is that you end up embedding into the bounded operators on L2 of G. But in our particular case, you can do a little bit better. You can do a little better. This actually extends to, well, the extension you always have, but the target you don't always have. You always end up in the C-star algebra of G. So this formal dimension is a secret weapon which allows you to take this classical formula from representation theory, from shear orthogonality, and pass it to infinite dimensions, and it all works out kind of beautifully. So these representations are very well known from a, I don't know, an abstract theoretical point of view, from the point of view of functional analysis. They have this wonderful, wonderful structure, and in particular, they have this really, really subtle and interesting formal dimension attached to them, which is a mysterious number. Okay? As you can see, even in the finite dimensional case, it's not a sort of universal invariant. It depends on a choice of Haar measure. And if you change Haar measure, the formal degree changes. So you should think of as this formal degree as not being a number. It's, if you think about it, it's a translation invariant density on the group, a translation invariant measure on the group. In that sense, it's a canonical thing. So each discrete series representation gives you a canonical Haar measure attached to it, canonical normalization for Haar measure. All right, very good. And so the theorem is not very hard. In fact, let's break this up into some little lemmas. Oh, one more, actually, let's do it this way. So going back, for all of this abstract stuff here, nobody cares if the group is connected or not. Nobody cares anything else about the group. But if G is, going back to our previous discussion, connected and has compact center, in this context, we defined a basic, which I was discussing just a moment ago, and that implies compact. So these representations, these basic representations, are all compact representations, and therefore they're all discrete series representations. And so they have interesting numerical invariants, these formal dimensions, a whole interesting package fitting together like that. There's a little definition that I forgot to give, so I'll give it now. An irreducible unitary representation of G is said to be admissible if the following thing is true. If it's, oops, wrong kind of bits. If it's K multiplicities. So we talked about these a little bit before lunch. You can attach a bunch of numbers to a representation by taking the Hilbert space of the representation and tensoring it with any irreducible representation of K, and then looking at the K fixed vectors. Actually, this is the and then you get a number. Here it is. This thing is a number. And these multiplicities are finite. So as it stands, this thing is some integer, or maybe infinity, but the condition is that these are all finite. According to convention, this is the multiplicity with which sigma star appears, the multiplicity of sigma star. Okay, and just continuing, I guess we can go over here. In fact, sorry for causing you dizziness. Just keep the natural order there. If you have a basic representation, then it's also admissible. Now, it's a fact that for the groups we're discussing, every unitary representation, every irreducible unitary representation in the whole world is admissible. So admissible is no big deal. But whether or not you make the effort of proving that theorem, it's certainly the case that these basic representations are admissible. And one final lemma is that you can turn all of these things around, namely compact plus admissible implies basic. And in all of this, we're talking about groups which have compact center. Is compact center and connected. Has compact center and is connected. So that makes these basic representations a little less mysterious. Now we know sort of what they are. Guys all look a little sleepy after lunch, maybe. The only person who's not asleep is me. And that's only because I would like to be sleeping, but I have to stand up here and talk. Okay. It's not so obvious. It's a little harder. This is not a general fact, but for our groups, in fact, it's the case that square integrable implies basic. These are exactly the irreducible square integral representations. Okay, but somehow a better definition. Square integrability is really a definition from, although it may not seem so, from measure theory, and it's not really related to not really appropriate for the topological approach we're taking to the tempered dual. A better approach is this compact version. Oh, one more thing. For our groups, indeed for a very much broader class of groups, basic is exactly the same thing as saying isolated in tempered dual. Different ways of looking at the same thing. So the tempered dual is some topological space. We're trying to understand what it is. It may contain some isolated points. Pop, 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 pop. And those are exactly the basic representations which any given group may or may not have. Okay. I don't want to say too much about all of these lemmas because they're really not very complicated. Give them numbers and decide if we want to say something about any of them. They're all fairly routine. I suppose you have a basic representation. Whatever that is, we'll remember what it means in just a moment. And now we want to show that that representation is compact. And so we have to build some ideal according to the definition. Oh, it's still there. According to the definition of compact, we have to build some ideal. So how are we going to build it? So we need to build some ideal, as in the definition, out of what? Well, you have a representation which is basic, and basic, the definition of basic has to do with some other ideal which involves compact operators. So it all seems pretty good. So the ideal in the definition is exactly the part ideal inside it, as it happens. Subideal. In fact, it's a direct summand. that act as the zero operator on all. So I could have said that another way. It's the intersection of the kernels of every single tempered unitary representation that G has, except for pi. Okay? And that makes it a sub-ideal of the basic ideal, so it consists basically of compact operators, at least acting on each of those spaces, L2 G sigma. And you can check that this ideal is isomorphic, as it should be, to the compact operators, as in the definition. Boom, Bob's your uncle, you have the ideal. So that's just how it's done. And all of these other things are more or less the same. Let's maybe just look at admissibility. Remember that L2 of G is a Hilbert space which contains, it's a completion of the compactly supported functions on G, completed not into an algebra, not into a C-star algebra, but completed into Hilbert space, okay? And of course, the C-star algebra is acting on L2 of G, and L2 of G falls apart into two pieces in exactly the same way that the C-star algebra falls apart into two pieces if you're given a basic compact representation. If you have a compact representation of a C-star algebra, this one here, then in particular the C-star algebra is a direct sum of 2 bits. And what that means is that every representation of the C-star algebra is a direct sum of 2 bits, one of which is a representation of one summand, and the other of which is a representation of the other summand. And so each time you have such a decomposition of a C-star algebra and a representation of that C-star algebra, then the thing will break, the Hilbert space will break apart into some subspace plus an orthogonal complement. It's not very deep. And what this does is it gathers, this is just a multiple of the representation pi, and this contains no copy of pi. Okay. And now you can say it's very, very easy exactly what the first part is. The first part. Pi part, which is the part of the Hilbert space on which the kernel of pi acts as 0. Yes, good. As a representation of pi, it just looks like h pi with multiplicity h pi star. In fact, this is true as a representation, not just of one copy of G. G acts in 2 different ways on L2 of G by left and right translation, and this is exactly what happens to the pi part as a representation of G times G. So what you see is that h pi occurs in the regular representation. With multiplicity, well, just the dimension of h pi, which is almost always infinite, if the group is not compact. But more to the point, it occurs in one of these constituent spaces that we decompose according to the representation K. It occurs in this space here with multiplicity that I wrote down before, which is M of, well, the way I did it, sigma star, which is equal to multiplicity sigma. Okay, oh no, take that back. But, one final but. We're trying to understand lemma 2, which is about admissibility. Did lemma 2 disappear? Oh no, it's still up there. And so I need to know that a basic representation is admissible. If I have a basic representation, then the C-star algebra is acting as compact operators on the intersection of this space with the pi part. And so the representation can only occur with finite multiplicity. If you take a single operator and you take an infinite direct sum of itself, it's not going to be compact anymore. So basic implies exactly that all of these multiplicities are finite. Because basic is about something is acting as compact operators. But if I have a representation with infinite multiplicity, then the group cannot act, or the C-star algebra of the group cannot act by compact operators on that infinite multiplicity representation. All right, so these things all fit together rather nicely. What was 3? Compact plus admissible implies basic. This is very, very simple. It's no harder than these two things here. Let me just leave that out. These are all very routine. Nothing, we're not exercising ourselves much, getting a little sleepy because these are not very interesting things. The point is that this basic ideal consists of representations which are, in some sense, very familiar. They play an important role in the work of Harishchandra, these square integral representations, and that's all it consists of. And so we have a very precise control of what this basic ideal is. And the rest of the C-star algebra of G, the rest of the tempered dual of G, the non-basic part, is all about these homogeneous spaces G mod n. It's all about relationships between the group G and the group L and so on. It's a part that we can hope to understand in some inductive way by understanding L first as a block diagonal subgroup of G and applying that understanding to understanding G. Okay. There's a part of the representation theory of G which is sort of irreducible, irreducibly complicated. You cannot understand those representations, at least in a naive way, in terms of smaller groups, for example, as induced representations. Those are the ones that are discussing here. These basic representations do not come from smaller groups inside of G. The basic ones have to be understood on their own terms, using a whole different set of techniques. But then there are the non-basic representations, which we hope to understand, so to speak, by induction, by pretending that we all understand all groups of real rank 11, let's say, as I said this morning, and using that knowledge to understand all groups of real rank 12, and so on. All right, very good. I made a few notes. Yeah, maybe just a couple of remarks. Maybe we'll put one little remark here. This is a fun exercise to work out these calculations in this form, I guess I do to Harishchandra. Let's choose a basic, let me show you some basic representations. These turn out to be the only basic representations of this group. And it's convenient to choose a different model for this group, SU11. So this is the group of all 2x2 complex matrices. Oops, let me write them down explicitly. Group of all 2x2 matrices which look like this. There's an alpha and a beta bar and an alpha bar, and there's an equation which says that alpha squared minus beta squared, the determinant, is equal to 1. So that's the group. And it's an exercise to show that it's a three-dimensional group. You can easily count dimensions here. 2 complex numbers, but 1 real constraint, so it's 3 dimensions. And it is a copy of SL2R. And here's a little lemma. Well, first of all, note, here's a function which associates to a point on G. Just the number alpha. So it's just a matrix, literally a matrix coefficient function on G, and it's nowhere 0. Because alpha squared is always 1 plus beta squared, so it's certainly bigger than 1. Okay, and it's a little calculation, not so easy. But if you take alpha to the k, raise alpha to the kth power, let's make k positive, so I'll write alpha to the minus k like that. then this is an L2 function, as long as k is at least 2. Alpha itself, or 1 over alpha, is not an L. Alpha is an unbounded function, goes like this to infinity. But 1 over alpha is not decaying fast enough to be an L2, but alpha to the minus 2 is. And another calculation is that if you look at the span of these combinations, let's take alpha to the k, get this right, minus k minus, I don't know, j, and then beta to the j. This is the span of a collection of L2 functions. So we've seen that alpha is alpha to the minus 2, for example, when k is 2, is an L2 function. If you think about it for just a moment, all of these are L2 functions because the size of this monomial in alpha and beta is no bigger than the size of alpha to the minus k, which is in L2 thanks to this relationship here. And this span of these guys, the closed span, is an irreducible subrepresentation. Of L2G. So there you go. There's the most brutal way of showing a representation. And another calculation. So this is a square integrable representation. Easy to check that this is compact. All right, very good. So in 2 weeks, after the holiday, hope to say something about how to classify compact representations in general. But for now, classification, that requires a completely different set of ideas. So we'll just have to leave that topic behind for now. Oh, maybe I'll say just sort of a half theorem. So here's the theorem of Harish-Chandra. It applies when G is connected and that's all you need. Oh, let's continue to talk about compact representations. Make the center of G compact as well. So when does G have compact representations? In fact, let's do it this way. Here's half of Harish-Chandra's theorem. This is actually if and only if, but I'm only interested in this part for the time being. Here's what I want to do. I want to take the centralizer in G of any maximal torus in K. And the criterion, in fact, this is an exact criterion of Harish-Chandra's. This is compact. This is if and only if. Okay. I mentioned this theorem because it's very similar to things that we're about to see, and although it's infuriatingly difficult to prove this theorem, I do not know a simple, beautiful, geometric way of proving this theorem. and I feel that, that I'm missing something. And so a challenge is to find a geometric proof which is similar to the geometric proof, which I haven't given yet, similar to the geometric proof of the main theorem about L2 of G mod n and so on that I mentioned in the morning's lectures. Okay. The theorem of Harish-Chandra is, the proof of Harish-Chandra is very, very beautiful and ingenious, and it uses some ideas from abelian Fourier theory, abelian harmonic analysis in a very, very clever way. It's a gorgeous argument, very high class, very sophisticated. It's an argument that you would like to take with you to a very fancy restaurant and discuss it with your friends, because it looks like you're very clever to discuss this very sophisticated argument. But I'm asking, is there a very simple argument that you can show to your friends in McDonald's, something just very simple and down to earth? Okay. All right, and now I think I want to, yeah. I want to say something about some of these words here. So what happens if you have a group without compact center, like GLNR, for example? Or maybe a group which is not connected, also like GLNR. What happens if you're dealing with these groups and you want to break up the representation theory into two parts, some sort of basic representations, and then the representations associated to L2 of G mod n? How should you do that? What's the correct notion of basic representations? It's different from the basic, from the notion we had before. If you have a group which is connected, and you want to prove a collection of theorems and lemmas and so on, like the ones I've been discussing here, then the appropriate notion replacement, let's say, for compact is what's called compact modulo center, which is a counterpart of what people call square integrable modulo center. And let me just say a couple of words about this. There's a fancy way of saying what I'm about to say, and there's a not so fancy way. And the fancy way is this. If you have an irreducible representation, and if you restrict it to the center of the group, then what you get, according to Schur's lemma, is a character, a one-dimensional, a multiple of a single unitary character of that representation. And unitary characters are exactly what I want to describe here. Suppose I have a homomorphism from alpha into the one-by-one unitary matrices. If I have a group with compact center, it may still have such homomorphisms, but it's not likely to have very many. But here is what I should like to do. I want to build a version of the C-star algebra, which involves alpha here as a sort of twisting, and it acts on, maybe I should have started with this, a version of the L2 space. And I'll leave it to your imagination what exactly the definition of this is. It will be obvious once I've told you what the Hilbert space is. So this is exactly the set of functions on G. Oh, I screwed something up here. I want to put here the center of G. Apologies. Now it will make more sense. Which behave on the center in exactly this way. And the L2 norm on this space. These functions are not square integrable because they have constant modulus in the center direction, which is not compact. There's no hope for these things to be square integrable. But on the other hand, this is a perfectly well-defined integral that I'm writing down here. We can integrate over G divided by the center, the absolute value of f of G squared dg, like that. The modulus of f of G squared is independent of choice of representatives in this coset space, and so we can define a Hilbert space in this way, which involves a twisted version of the L2 functions on G modulo its center. It's a fact that when you take one of our reductive groups and you divide it by its center, you get a group which has compact center. It's not completely obvious, because there are certainly groups with the property that when you divide them by their center, they become abelian, so they have lots of center left. But that's not the case with these groups. When you effectively divide by the center, you get a group which has no center at all, or a compact center, and so it's kind of an interesting construction. Anyway, if I have a function which has this property, I can convolve it against another function which has this property, and so I get an obvious algebra of functions here acting on functions here. Okay, and now I can do the following thing. I can consider the irreducible representations of this C-star algebra. These correspond to irreducible unitary representations of G, which are tempered and which have the property that when you restrict them to their center, they behave like the character alpha, just like you see up there. Okay? So the representation theory of this C-star algebra is a piece of the representation theory of G. It consists of only those representations of G which have a certain central character, namely the central character alpha. Okay? And you can just knock yourself out if you want to. This whole story goes on for a bit. These spaces that we were discussing have alpha twisted versions. If you think about it, any character has the property that when you restrict it to n, maybe I should say n intersected with the center. Well, you have to say it like that. There is nothing in this intersection. It's a one-element group, so alpha restricted to it is certainly the trivial character. And so now you can get a correct formulation of the main theorem. Namely, if you have an irreducible tempered representation with central character alpha, there's a dichotomy. Either it's weakly contained in one of these guys, or it is alpha basic in the sense that it acts compactly on L2 of G alpha, sigma, for any irreducible representation sigma, and blah, 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 blah. Okay, that's all I want to say. Oh, and it's a true theorem. Oh, and alpha basic representations are exactly the same thing as square integrable, as compact or I should say alpha compact. Maybe I should just write that down. So you could introduce a character on the center throughout the entire discussion that we had all throughout the morning and all up to now, and nothing would change, and you'd prove a more general theorem just with alphas everywhere. Okay. That would be the classy way of dealing with this. Alternatively, you can save yourself the bother, because the groups that we're dealing with fall apart in a very, very pleasing way into two bits like this. There's a bit that I'll call M. It's a Cartesian product of groups, and there's a bit that I'll call S, let's say. So S is just the center of G intersected with X of P from this morning. So it's the part of the center consisting of positive definite matrices. There may or may not be positive definite matrices in the center, but if they are, they form what's called S. This is always called the split component of G. And there are various ways of explaining what M is. It's the subgroup of G generated by all the compact subgroups of G. Another way of saying that is that this is the intersection over all phi of the kernel of phi mapping G to this particular group of positive multiplicative reals. For example, suppose we take GLNR. Inside of GLNR, there are the matrices which have determinant plus or minus 1. That's exactly what M turns out to be. And then there are the positive multiples of the identity matrix. That's what S turns out to be. And it is the case that every matrix in GLNR decomposes into a matrix which has determinant plus or minus 1 times a positive multiple of the identity. And that's universally true in these groups that we're talking about. They all fall apart in this pleasing way. And the whole thing about this whole construction is that this fellow now has compact center. Okay. And so every group either has compact center or does not have compact center. But if the center is not compact, it's only not compact for a stupid reason, because somebody multiplied this group against a big abelian group. And to understand the representation theory of this group is a piece of cake, because it's just every representation of this product is just a tensor product of a representation of M, which is tricky, times a representation of this abelian group, which is easy, just a one-dimensional character. So extending to groups with non-compact center is very easy, because every group is a product of a compact center group with some abelian group in a canonical way. This is true for our groups, our connected real reductive groups, the ones we're talking about right here. But if you wanted to do that by the book, so to speak, you'd follow this alpha twisted method. A little bit about disconnected groups. The main reason I want to mention this is, well, first of all, you can't avoid disconnected groups, but if you ever look in the works of the reductive or semi-simple representation theorists, you'll see some mysterious conditions placed on the groups, and I'd just like to explain why those conditions are there. Here's a particular group. Let's take the two-element group and let it act on the real line in the obvious way by sending x to minus x, and then form the semi-direct product. So this is an example of a reductive group, according to our definition. You can realize it is almost connected, and you can realize it as a group of matrices closed under the transpose operation. Pretty easy. But it's complicated because this group is basically abelian. It's abelian plus some stupid element of order 2. It's basically an abelian group, but on the other hand, the center of G is trivial. So there's no point in looking for the center here, because there isn't one, for a really stupid reason. And there are other things which are annoying about this group. This group is so thin and uninteresting that it has none of these unipotent subgroups n whatsoever. It has no parabolic subgroups. And so if you were attempting to reformulate our theorem in this example without thought, then you would come up with a wrong theorem, which would say that every irreducible representation of this group is a square integrable modulo center representation, because the other alternative involving the subgroups n doesn't exist, because there are no n's. Okay, but it's not the case that every representation of this group is square integrable modulo center. No representation of this group is square integrable modulo center. So there's something a little bit wrong here, and the resolution. First of all, the problem is this, that the center of the connected component of the identity is not central in G. And in standard representation theory, this is exactly what you make your definitions to avoid. So definitions are made to avoid this phenomenon. There's something called the Harish-Chandra class. And the Harish-Chandra class consists of reductive groups of the sort that we've been talking about, which have the additional property that, or which have a condition which guarantees the additional property that each time you have either G or one of these Levy subgroups L, anything which is in the center of this, the component of the identity is indeed central in G or in L. And that makes life incredibly much more simple. And you need something, as this bad example shows. In this world, maybe I'll just use this little piece here. I'll go in some logical direction. Rather than restrict the groups in that complicated way, this idea of basic representation, or its equivalent formulation in terms of compact representations, needs to be replaced by the following thing. If I have any irreducible representation of G, I can always restrict from G to the connected group, which is the component of the identity. And when I do that, I'll get a representation which may not be irreducible, but it's always a direct sum of finitely many irreducible representations, because there are only finitely many components. And there is a version of our basic geometric theorem, our fundamental geometric theorem, the one that's not this one here, where did it go? The one that I was mentioning when I was discussing this. And, but the basic representations which arise, the representations which are not weakly contained in any L2 of G mod n, they turn out to be these representations here. They are those representations which restrict to a direct sum of compact modulo center miscible representations. I'm not going to say more about this except what I just said. If a group is not, let me just summarize, if a group is not connected and does not have compact center or does not have compact center, then the representations which cannot be obtained from smaller groups, the ones which are not associated to any Levy subgroup, are those which are either compact, in the simplest case, or compact modulo center, or in the most general situation have this property here. So there are versions of all of the theorems we've been discussing up to now in the general case, but the fundamental representations, the basic representations from which all others will be built, the ones which cannot be built from a simpler process, are these ones that I'm mentioning right here. Okay. And if you read in the books about groups in Harish-Chandra's class, and you wonder what is that about, it's exactly the condition which allows you to replace this complex statement here by the simpler statement, which is just compact modulo center. This is equivalent to compact modulo center for one of the groups in Harish-Chandra's class. Every group which is a component of the group of real points of a connected complex group is in Harish-Chandra's class. So all of the ones that you know, as long as they're, they have an S in front of them, are examples of groups in Harish-Chandra's class, SOPQ, and so on. Even though it's not a connected group, it still belongs to Harish-Chandra's class. All right, very good. Be careful there. Let me not waste time on that. Any questions? Are you ready for more, or are you just, can you take a little bit more? Thanks. Still strong? All right, let's say a little bit more. Oh yeah. So my intention today, this afternoon, as I said at the beginning, was to discuss the basic representations, the representations which are not attached to any L2 of G mod n. And now I've done it. They're exactly, in the simplest possible case, they're exactly what Harish-Chandra would call discrete series. And in the most complicated case, this is what they are. And now let me say more about the representations attached to parabolic subgroups. And a lot of what I want to say, I already said a week ago. And what I said a week ago, we can now do, again, in much greater generality, although it's, there's no new idea, it's just the same thing. So we built some object which was a Banach space, a completion of the compactly supported functions on G mod n. It was a Banach space, in fact, one of these C-star modules, and we do it in the following way. If I have two functions on G mod n, scalar functions, then I can build in a product which is valued not in scalars, but in this C-star algebra. So it's a function on L, or it's something in the algebra that you get from completion of that. And here's what the function is. It sends L, and what I'll do is I'll take F1, and I'll take F2, and I'll translate it on the right by L. This is the translation operation that we discussed earlier today. And I'll take the usual L2 in a product. When I do that, I get a scalar. So this is a scalar function on the group L. And if you start off with functions which are continuous or smooth and compactly supported on G mod n, then what you get here is a compactly supported function, because L is acting properly on this space. And if I have two functions, and I translate one of them by L and keep the other one fixed, eventually their supports will be disjoint from one another, and so their inner product will be 0. This is a compactly supported function, so it belongs to the C-star algebra. which is a completion. And it's one of these correspondences that we were talking about last time. So G acts on the left, that action passes to the reduced C-star algebra, and that action is through compact operators in this fancy C-star module sense. Just like before. So to make this a sensible definition, we need to know that L acts in fact, freely, but the critical thing is properly on G mod n. The critical thing here is that if I take G mod n and I divide it by L, maybe I'll write down one formula here. Suppose I have a function on G. This function defines an operator on this module, and it's worthwhile to write down what it is. This is basically a Banach space of functions on G mod n, some completion of a space of functions on G mod n. And this operator is given by a kernel. That's in the sense of integral kernels, depending on f. So it's an integral operator, and here's what the kernel is. You just integrate over n. You can do a calculation. You'll see this is correct. Of f of G1 and G2 inverse left there. The space G mod n is not a compact space, so this is not an integral operator in the most classical sense of the theory of Hilbert and Schmidt. It's an operator given by whose Schwartz kernel, if you like, is this thing here. But it has a certain property. So on the space G mod n, the group L acts on the right, and I could stick an L on the left on one slot, or I can stick it on the right on the other, and it's fun to calculate to see what happens, and I forgot to do the calculation before I came, so there's a sign which is either plus or minus 1 in this formula. Everything is right. Well, the sign is correct as well, because I didn't specify. So this thing k is, I mean, it's a function. It starts out life as a function on G mod n times G mod n. But you can also think of it as just a section of some line bundle. Over the space you get by taking two copies of G mod n. I'll do it this way. The other copy n mod g. No, changed my mind. It's G mod n2. And dividing by L. This thing is compact. If you have an operator given by an integral kernel k of xy on a compact space, an actual integral kernel on an actual compact space, then what you get is a compact operator in the actual sense of compact operators. Here, if you have an operator which is given by an integral kernel, which is a section of some line bundle over this compact space, then again, it turns out you get a compact operator, but in some fancier sense, the sense of this Hilbert module, C-star module theory that I was talking about. Okay, but I just wanted to point out that somewhere there is a compact space floating around. And let's try and restore the usual order here. Oh, yeah. So last week when we were looking at this construction in the special case of SL2, where G mod n was the plane, take away the origin, we figured out exactly what the irreducible representations were, which are weakly contained. In L2 of G mod n. There was some trick. There was an elementary lemma in C-star algebra theory that we wrote down, cited from Dixmier's book, and using this compactness here. And there's a little asterisk here, which I'll come to, a little footnote, which I'll come to in a moment. These are exactly the summands of parabolically induced representations. And what you can do is you can take this module and use it to induce representations from L to representations of G in this way. So here pi is reducible representation. And I just wanted to, as an asterisk, say that if we assume that every reducible representation of C star of L is admissible, the condition that we had earlier, then every one of these induced representations is completely decomposable. It's a discrete algebraic or Hilbert space theoretic direct sum, orthogonal direct sum of irreducible representations. So no continuous decomposition, nothing like that is needed. It's just completely decomposable. But of course in the Hilbert space. And another remark, good exercise actually. Lots of definitions. This construction as a balanced tensor product is a kind of a difficult thing to think about, but in fact, this is equal to a much more concrete space. This is isomorphic to just functions from G into H pi, which satisfy a condition that's familiar from induction theory, namely G f of GLN is equal to basically f of G with L acting on it. Except there's a funny thing you have to stick in here, which is the square root of delta of L, minus L like that. This is called unitary parabolic induction, which is the thing that George Mackey discovered was the generalized version of those representations on RP1 that I mentioned earlier. So on the right-hand side is the functor of unitary. Unitary means this factor is included, parabolic induction. It suggests that this thing is a unitary representation, indeed that it's a Hilbert space, and so it is. The inner product for this induced representation, which is usually written like this, is just the integral of f of f1 of k inner producted with f2 of k. This is the inner product of k. So that's, as it happens, a unitary invariant inner product on this vector space. Of course, after you should start off with continuous functions and then complete to get an L2 space. Okay. There's one thing we can say now, today, this afternoon, that we could not say last week, which has to do with the fact that if we're dealing with a group which is more complicated than SL2, then we can consider examples where L itself has interesting parabolic subgroups. In the case of SL2, there's really only one parabolic subgroup, and the L is an abelian group. It has no further parabolic subgroups, but in general, that's not the case. So suppose I have a parabolic subgroup. To say that A is, P rather, is standard means that, remember from this morning, we chose, first of all, this maximal abelian subspace A, and then we exponentiated, got some abelian group of positive definite matrices, and inside of that abelian group of positive definite matrices, we chose a Weyl chamber. We chose a particular way of constructing parabolic subgroups in such a way that after you've chosen an appropriate basis, N consists of block upper triangular matrices, and L is block diagonal matrices. We made some choices to standardize the construction so that A became diagonal matrices and N became block upper triangular matrices, L became the corresponding block diagonal matrices. And anyway, the A, which I was just discussing, sits, if you think about it for a moment, inside of L. L was a certain centralizer group. It was a group of elements in G which was centralized by a certain one-parameter group, which was a one-parameter group in A, and A is abelian. So A certainly sits inside of L. So for L, we can take this very same A that we already took for G, right? And we'll And this A plus, which we built with regard to G, in reality, it usually comes by thinking about, it does come by thinking about a little bit of Weyl group combinatorics. the A plus for G may not be the same as a suitable chamber, Weil chamber for L, because the normalizer for L may be a lot smaller than the normalizer of A plus inside of L. A inside of L may be a lot smaller than the normalizer in G. However, we can determine a unique preferred choice of chamber for L once we've chosen a chamber for G. And it'll just be a union of chambers for G. All right. And now suppose we have some, what should we call it, R U. Now we can talk about standard parabolic here. So again, I'm thinking of L as block upper triangular matrices, and what R consists of is a subgroup of block L consists of block diagonal matrices. R also is a block diagonal matrix subgroup with smaller blocks. Inside of each big block for L, we've chosen some smaller blocks for R. And U in each of those blocks for L is some block upper triangular matrix. Draw a picture. Maybe G looks like all big square matrices like this. And then maybe for L, we chose matrices which are block triangular like this. And then maybe for for R, we chose some even smaller blocks, maybe like this. So what I'm drawing in yellow is a parabolic subgroup of L. Let's give it a name, Q or something. On the other hand, L I was drawing, maybe I'll say P. There's an obvious way of building a single parabolic subgroup of G out of this data. Namely, it's the parabolic subgroup consisting of matrices which are 0 below this line. All of this stuff in yellow plus all of this stuff here. So you can join together parabolic subgroups to get new parabolic subgroups in that way. Namely, you can form, well, let's just not give it a name, R times U times N. This is now a parabolic subgroup. Standard again, parabolic subgroup. And it won't surprise you at all to learn that if you induce from Q to L, let's do it this way around, some representation of R to get a representation of L, and then you induce from P to G, that thing. That's the same thing as inducing all the way from RUN to G, H pi, just in one go. I mean, how could this not be true? And it is true. Now we can put everything together and get this rather beautiful theorem of Harish-Chandra. So at the very, not at the very beginning, but in the course of the last lecture, I mentioned some sort of, I don't know, basic fundamental theorem in which I defined, we studied this basic ideal, the intersection of the kernels of the lambda G mod n's. And that's a slightly complicated geometric theorem, which I'll explain, I hope, in just a moment. But everything I mentioned after that is just kind of just plodding along. It's not difficult at all. It's just juggling definitions. This is just juggling definitions. It says that the C star module for P tensored with the C star module for Q is the C star module here, these C star G mod n modules that I'm talking about. And you just write down the obvious map and it works, okay? And I said that a basic representation for a compact and connected group is the same thing as a compact representation. And you just make the obvious arguments and it works. There's nothing complicated that we've done today at all, except state that geometric theorem earlier on that we have to get back to. And what we get as a consequence is this rather beautiful result, which I'll call the Harris-Chandra principle. Which explains the general shape of the representation theory of a reductive group. And it's cleanest if we assume that G lies in Harris-Chandra's class. It may not be connected, which would be enough, but otherwise, let's assume it lies in Harris-Chandra's class. This condition is what we mentioned it a little bit earlier, and what it allows you to say is that basic is exactly the same thing as compact modulo center. And the conclusion is that every irreducible tempered representation of G, these are the things we want to classify, is contained, is a sub-representation of the parabolically induced representation. There's a construction called parabolic induction. But once you understand it, you understand everything, as long as you understand what you're parabolically inducing from. Of a compact mod center representation of some Levy subgroup, some block diagonal subgroup. In this theorem, I'm using the convenient fact that G is a parabolic subgroup of itself. So one possibility is that the representation in question is compact modulo center, and you're not actually doing any parabolic induction at all. That's included in this statement, because parabolic induction from G to G is just do nothing. Okay. Here's the idea. I have a representation. Maybe it's one of these basic representations, or it's not. If it's basic, then it's compact mod center, according to what we said. Stop. If it's not compact mod center, then it's weakly contained in one of those L2 of G mod n's. And according to what we were just writing right here, if it's weakly contained in one of those L2 of G mod n's, then, by the argument that we went through last Friday, it's actually parabolically induced from something, or a sub-representation of something parabolically induced from something. Now, what about this something representation? It's a tempered, irreducible representation of L. And it is either compact modulo center, or it's parabolically induced from something even smaller by applying the very same argument to L instead of G. And we can keep continuing. And so what we find is that in the end, the process is going to end. There are only a finite number of parabolic subgroups. In the end, every representation is going to be parabolically induced from, exactly as I said there, a representation which is compact mod center, a discrete series representation, a square integrable representation, modulo center, or is a sub-representation of such a thing which will always be discretely decomposable. So the discrete parameters which describe representation theory are the irreducible compact mod center representations of, so modulo the center, I guess the parameters are discrete, of G, and the continuous parameters come from the center, the variation of the center. It's a very nice result, which organizes the representation theory in a very, very simple way. And it tells you it's absolutely essential to know what the compact representations are, and because they're what are responsible for everything. Remember, compact modulo center can be reduced to compact if you have a reasonable group, because every group is a product, a Cartesian direct product of a group with a compact center times a group which is abelian. Okay. Some Rn. So this was the goal for today. One thing is missing, which we still have time to get back to, which was further discussion of that basic geometric theorem. I just want to check, see if there's anything else I want to say before getting to that. Any questions? Ah, he's so good. Good student.
That induction
Yes.
is a tool to get a representation of big group
Yes.
from a representation from small group.
Yeah.
But why such composition is defined?
Okay, so
Yes, that's it.
yeah, the notation. Yeah, that's a good question. Make a little comment. So what's going on here is we're starting from a representation, not of P, but of its block diagonal part, L, as unitary operators on some Hilbert space. Now we are noticing, that L is a quotient of P. P is a semi-direct product of L and N. And if you divide out by N, which is a normal subgroup, what you get back is L. If I have an upper triangular matrix, the map which sends an upper triangular matrix to its diagonal part is a group homomorphism. It preserves multiplication. And so we can think of pi, if you like, as a representation of P. Like that. And now finally there's an operation, standard operation, which takes representations of any subgroup to representations of a big group. This is induction, the adjoint of restriction. And finally, we are, and there's just a little footnote, this funny character is appearing delta, so unitarily, I'm going to spell that right. Inducing. In the sense of Mackey, from P to G. So we are starting with a representation of L, not of P, but we are thinking of it as a representation of P, and then we're doing this operation, and we're ending up with a representation, well, in this particular case, a representation of G. Okay, so we go from representations of block diagonal groups to other representations of block diagonal groups, and we use the upper triangular groups as a sort of intermediate vehicle. Okay. And the reason we're doing this, why are we doing this strange thing? Why are we choosing this bizarre sort of pirouette, this strange maneuver to go from a representation of a block diagonal subgroup to a representation of all of G? Why do we do this funny two-step procedure? Well, we do it because it's sort of forced. It comes out of that geometric theorem, which we'll remind ourselves about in just a moment. It's not because we especially like this construction, but this is the interpretation in the language of representation theory of a certain geometric fact, which was the fundamental theorem that I wrote down at the beginning, which I'm going to return to now. Okay? You don't have to like this operation. You don't have to be attracted to it, you know, to want to study it, because it's forced on you by the geometry of the situation. It's the geometry which dictates to us that we should study this strange operation. But this explains the notation. You might say, why not start with arbitrary representations of P? Not representations which factor through this quotient. And why not induce them? Well, you can do that too, but they're not the ones which are essential to the whole story. The representations which are essential to the whole story you get by translating a geometric fact into representation theory language. And when you do that, the geometry tells you that these are the good representations to study. And the other ones that I just mentioned, where you take an arbitrary representation of P and you induce it to G, well, you can study those too if you want, but that's just confusing things. Then they're not fundamental to the story, at least as the story was told by Harishchandra. So we once again, I just repeat myself, there's a geometric theorem, which we'll now return to. That geometric theorem leads sort of inevitably to a whole bunch of definitions, like the definition of the C-star module, like the definition of parabolic induction, like the definition of compact representations. The theorem suggests many, many definitions, and then there are many elementary lemmas about those many elementary definitions. And what you end up with is this theorem, which is a translation of a geometric fact into the language of representation theory. Okay? Now, it's not the end of the story to know this theorem, because you certainly want to know what are the compact modular center representations. You want to actually write down parameters. And then you want to know, when you do parabolic induction of two different compact mod center representations, when do you get the same representation of G and when do you not get the same representation? There are many more questions to ask, but this is the big picture. And it comes from geometry, and now back to that geometry. All right. I'm worried about what I wrote there. What I wrote contained a small lie, but now that I've erased it, I won't go back and fix it. So I'm just going to repeat what I said before. Suppose we have a group with these additional conditions like SL2R. The theorem was a statement that the intersection of all of the kernels of all of these natural representations of G, or its C-star algebra, as operators on L2 of G modulo n, and the intersection is over, well, let's exclude G as a parabolic subgroup of itself, all proper standard parabolics. This thing here acts as compact operators. On every one of these spaces. This is this is a constituent, a sort of fundamental constituent from the point of view of K, a fundamental constituent, a multiplicity space inside of L2 of G. But geometrically speaking, L2 of G sigma is the L2 sections of some vector bundle over G mod K. some homogeneous vector bundle over G mod K. And to a first order of approximation, this space here is just L2 of G modulo K. That's what it would be when sigma is a trivial representation. So roughly speaking, this is L2 of G mod K. And I'm saying that if an operator is 0 on all of these L2 of G mod n's, then it's practically 0 on L2 of G mod K. Compact means very, very small, and practically 0 means compact. That's the basic theorem, which is not really a theorem, slightly a theorem about representation theory. It's not a theorem as it stands about irreducible representations, but a natural progression of events, a natural story can be told, which starts here and ends up with Harish Chandra up there. And that's the story that I tried to tell you up to now. So now let's return to this theorem. And for that purpose, let's return to the blackboard a picture from the first lecture. And so what I want to draw in this picture is, let's make it a little more elaborate by drawing in a second, or rather a third, sheet to the picture. In the language of, I don't know, geometric group actions, what I'm drawing is a family of coadjoint orbits here. One of them is G mod K, and I want to think of this one here as G mod KT. And all the way at the end here, I have G modulo K intersection L. This is, of course, a picture for SL2. And while I'm at it, I'm going to make a superhuman effort to make a decent picture here. Ooh, much better. Here's a picture of A+. This is a picture in the world of SL3. This 60-degree chamber. Maybe I'll draw it along here suggestively. So there's only one way to go to infinity. In the case of SL2R, it's, if you like, it's just a single ray like this. So what you see is a single ray, single direction going off to infinity here somehow has to be replaced by this fan of directions over here. So I mentioned that you can create a whole family of homogeneous spaces which interpolates between L2 of G mod, between G mod K and G modulo this particular space here. These two fellows are not completely different. At infinity, they are the same. In fact, a nice way of seeing that is that you can interpolate smoothly between them in exactly this way. It's interesting in this picture to draw in the base points. So if I write one of these pictures as a homogeneous space, G mod something, then of course I'm implicitly telling you that there's a preferred base point because there's a base point in this space, okay? And it's natural to think that the base points are somewhere here, but that's not the case. The base points are more, I don't know, something like this. And, all right, so let's think about the proof of the theorem. First of all, in the easiest possible case for SL2, where it's still an interesting theorem, and it's really no more difficult for SL3 or anything than it is for SL2. And for simplicity, let's just take the trivial representation. So this L2 of G mod sigma, it just means L2 of G. Sorry, L2 of G mod K in that situation. We don't have to worry about vector bundles, some auxiliary finite dimensional data. I'm just going to make it disappear by making this assumption. I suppose I have, so now N is the group of 2 by 2 unipotent upper triangular matrices. There's only one N to work with, and that's it. It's the only standard unipotent subgroup around. And suppose I have an F, which is an element of the C-star algebra, so it's acting as an operator on various spaces, the various Hilbert spaces that we see. It's an operator in this ideal in the C-star algebra. So F acts as 0 on L2 of G modulo N. On the cone, F, in some crazy way, is acting as the zero convolution operator. It takes some imagination to think about how